A modern CPU can execute billions of operations every single second, but on its own, it has a critical limitation. It possesses zero permanent storage. It cannot hold programs or data independently. To interact with the rest of the system, the CPU relies on precise physical pathways called the address and data buses. These electronic traces are the only way the processor can send or receive information. We define primary memory strictly by this physical connection. If a memory component is wired directly to these data and address buses, it sits in the primary tier. By contrast, secondary storage encompasses components that sit physically outside this immediate bus architecture. The CPU has no direct line of sight to these distant storage slots. Because of this physical separation, a strict rule governs computer architecture. Any data residing on a secondary drive must be transported across the system and loaded into primary memory before the CPU can even acknowledge it exists. This exact distance from the processor dictates the engineering of every storage component. The closer a memory chip is to the CPU, the faster it must operate, defining the system's entire memory hierarchy. This creates an immediate paradox the moment you press the power button. The CPU needs instructions to start doing its job, but the active memory is entirely blank. To break this deadlock, engineers built read-only memory, or ROM, into the motherboard as the first mandatory piece of primary memory. The defining physical trait of ROM is that it is non-volatile. The data written to it is permanently hard-coded at the factory, meaning the information survives completely intact even when the computer has no electrical power. Etched into this chip is a very specific set of initial instructions, known as the bootstrap loader, or system firmware. When power hits the system, the CPU reads this bootstrap loader first. These instructions tell the processor how to wake up the connected hardware components, and crucially, how to locate and mount the disconnected secondary drives. Looking at this image of physical memory sticks, we see the second primary component, random access memory, or RAM. This hardware is engineered specifically for high-speed active processing. But RAM is highly volatile. The moment electrical power drops, the circuits instantly clear, erasing all stored data. Despite this, RAM is essential. It temporarily holds the operating system and programs while running, feeding the CPU at the exact speeds required for rapid processing. ROM exists solely to solve the initialization problem at startup, retaining data without power. RAM solves the active execution problem, sacrificing permanence for raw speed. Achieving instantaneous access speeds requires expensive, complex hardware, which strictly limits the physical storage capacity of RAM compared to secondary drives. An operational crisis hits when the operating system and user applications demand more space than the physical RAM modules actually possess. To bypass this hardware limit, the operating system utilizes a software-engineered solution called virtual memory. When physical RAM fills up, the OS allocates partition space on the secondary drive as pseudo-RAM. Through paging, it ejects inactive RAM data to the secondary partition. This frees high-speed memory slots, allowing new active data to be loaded for immediate processing. But this creates a severe performance penalty. Accessing swapped pages on a secondary drive is far slower than querying physical RAM chips. Virtual memory trades system speed for capability. It prevents the computer from crashing when it runs out of physical memory, allowing you to run larger, more complex programs than the hardware alone could support. Because primary memory is read-only, or volatile, the system requires a dedicated tier for massive, permanent data retention, disconnected from the CPU, secondary storage. As we can see in this view of an open hard disk drive, the first major physical encoding method is magnetic storage. This is a mechanical architecture. It relies on physical platters divided into microscopic tracks and sectors, rapidly spinning under a mechanical read-write head. To encode data, electromagnets on that head alter the magnetic polarity of individual particles on the platter, locking them into north or south states to represent binary ones and zeros. This cross-section diagram illustrates the second physical encoding method, optical storage, the technology behind CDs, DVDs, and Blu-ray discs. Instead of concentric circles, optical media stores data along a single, continuous spiral track running outward from the center of the disk to the edge. A laser reflects off flat areas called lands and scatters when it hits indentations known as pits. A sensor reads this difference in light reflection to determine the binary state. Blu-ray discs achieve much higher capacities than DVDs by using a blue laser. Its shorter wavelength allows engineers to carve tighter tracks and significantly smaller pits, packing more data into the exact same surface area. The final and most modern physical encoding method is solid-state storage, found in SSDs and USB flash drives. This revolutionary modern method eliminates mechanical moving parts entirely, relying strictly on semiconductor physics at a microscopic level. Solid-state drives utilize specific logic gate architectures, primarily NAND or NOR flash memory technology. These drives use microscopic transistors acting as control gates and floating gates. By trapping electrons within these isolated gates, the drive maintains a static binary state permanently without requiring a constant power supply. By manipulating magnetism, focused lasers, or trapped electrons, secondary storage prioritizes enormous, permanent capacity over the raw speed required by the processor. Looking at this block diagram of the system's memory architecture, we can trace the distinct pathways separating the primary and secondary zones. When power is first applied, the CPU reaches directly into the non-volatile ROM, pulling the exact bootstrap instructions needed to initialize the dormant hardware. The firmware then accesses the secondary storage drives, grabs the operating system, and begins copying it across the system into the volatile RAM. Once loaded into high-speed RAM, the operating system and your applications feed instructions directly to the CPU via the data and address buses. The golden rule of computer architecture remains absolute. If the CPU is processing data right now, that data must be located in primary memory. Every component in this system represents a calculated engineering trade-off. You sacrifice permanence for speed in RAM and sacrifice speed for massive capacity in secondary storage. To test your knowledge on these specific memory architectures and prepare for your exams, review the practice diagnostics available at www.studybuddy.tech.